You've made it. We're on the very last video in the multiple regression series, where we'll look at a concept called multicollinearity. So by the end of the video, you'll hopefully know what that is, recognize when multicollinearity might be a problem, and be aware of what is or what is not appropriate to do with your multiple regression results when strong multicollinearity is present. So multicollinearity, also called collinearity, is when some of your predictors are strongly correlated with each other. Although I haven't named multicollinearity by name up until this point, we did have a safety net against this problem, because one of the very first things I showed you how to do was to make a scatter plot matrix and correlation matrix between all of your variables. And we checked to make sure that none of the predictors had correlation coefficients whose absolute value was any larger than 0.7. So this was to limit multicollinearity from happening. The problem with multicollinearity is if you have predictors that are strongly correlated with one another, if you change one predictor's value, it's going to kind of spill over into the other predictors that it's strongly correlated with. So it's like that, the butterfly effect. So one little change in one place could cause enormous changes all over. This is going to make the partial slopes in our model very volatile. Just moving a couple data points could cause a dramatic change in the partial slopes. Sometimes they'll even be negative when you thought they'd be positive, or vice versa. So pretty much anything involving, knowing or estimating or testing the true value of those partial slopes is not a good idea when strong multicollinearity is present. Let's take a closer look and see this in action. So I'm going to use a data set called CARS 2015. So we'll be trying to predict the highway miles per gallon of different cars. And some of the predictors we could use would be the weight of the car in pounds, the time in seconds it takes the car to accelerate to 60 miles per hour, and the time it takes the car to drive a quarter mile on the racetrack. So let's make that scatter plot matrix and correlation matrix, see which variables are strongly correlated, and does the direction of those correlations make sense based on what we know about cars. So remember, for the scatter plot matrix, we go to Analyze Multivariate Methods, Multivariate. And at this point, although we are going to be predicting highway miles per gallon, we don't have to designate that. We just throw everything in here. All right. So the strongest, we have some strong correlations. There's a strong negative correlation between highway miles per gallon and the weight of the vehicle. Now, does that make sense? If someone driving a Hummer, a big, massive, heavy vehicle, is probably going to get worse gas mileage than someone driving a Toyota Civic or Toyota Corolla, something like that. So as the weight goes up, it makes sense that the fuel economy would go down. So a negative correlation makes sense there. How about these positive correlations? Now, keep in mind, these are the time to get up to speed or the time to race a lap. So a more economical or sluggish car is going to take longer. So does it make sense that as it takes longer to get up to speed, your fuel economy is going to improve? Yeah, so a car that sips gas might not be the fastest, but it's going to get a lot of miles per gallon. Whereas something like a Corvette, you might accelerate really fast, but it's going to burn gas a lot more quickly. So those directions make sense between each predictor and the highway's miles per gallon. When we look at the correlations among our predictors, we see a couple that are weak negative. That's fine. But we see a very strong positive correlation between the time to accelerate to 60 miles per hour, and the time to drive a quarter mile. Very strong, almost 1. So that's well above our rule of thumb of 0.7. So if we're obeying the rules, we would pick either quarter mile or acceleration to 60 and toss the other one. Today, though, let's be bad. Let's find out what happens if we keep them both in there. All right, so let's go fit a model to predict the highway miles per gallon using all 3 of these predictors. This is about the extent of my rebelliousness. All right, so we run that. Just, scanning our output. Nothing looks to be, out of the ordinary so far. Our residual by predicted plot looks like a pretty random scatter. No curvature there, no massive funnel pattern. We do have a little bit more narrowness off to the left of the plot, but that seems to be more just a symptom of having fewer vehicles with really low miles per gallon there. We've got a reasonably high R squared, and the F-test says that this model is useful. Looking at our parameter estimates, only one of our predictors seems to be significant, the weight of the vehicle. The other 2 things don't seem to, they're not significant at the 5% level. Okay, so if you just looked at like a quick look like that, it looks like nothing problematic. But let's maybe try to interpret one of our partial slopes and take a look at what our prediction expression would be. So I copied this table into my slides. All right, so this is just a simple first order model. We didn't include any interaction. We didn't need to add any dummy variables. So just basic model here. So we have our intercept, partial slope times the weight, partial slope times the acceleration, and partial slope times quarter mile. So for the weight, it's a negative estimate for the beta coefficient. So that makes sense, right? We said there was a negative correlation between weight and highway miles per gallon. How about this partial slope for the acceleration, though? So that one's negative as well. So if we were using our template for interpretation of a partial slope, we'd say that for each additional second that it takes to accelerate to 60 miles per hour, we predict a decrease of this much in our highway miles per gallon, provided that we hold the other predictors, the weight and the quarter mile, constant. Think about that for a second. So the longer that it takes to accelerate, we predict the miles per gallon is going to go down. But we just said on our scatter plot matrix that there's a relationship between acceleration and highway miles per gallon should be positive. We had positive 0.5175 as the correlation coefficient. So the sign of the correlation here should match the sign of the partial slope. For weight it did, it was negative. For quarter mile, I think that one was positive. Yeah, positive 2.57. But for acceleration, it was actually backwards. So if you get a partial slope like that just doesn't compute, doesn't make sense, that's a classic symptom of multicollinearity. Everything we know about multiple regression so far says that should have been a positive partial slope. So what's going on here, and think about our interpretation on the last slide, is we said that we wanted to increase the acceleration time by 1 second and hold the other things constant. So could you hold weight constant and find a car that takes one more second to accelerate? Yeah, probably. But could you have a car that takes one more second to accelerate and has no change in their quarter mile time? No. And think about it probably takes about a quarter mile to get up to 60 miles per hour. So they're almost the same thing, reflected by the really strong positive correlation coefficient. Right? So they're so tightly correlated that it just becomes impossible to hold one constant while changing the other. All right. So multicollinearity doesn't mean that your model is garbage and needs to be thrown out, and you can't use all your predictors. But it does mean that you can't really interpret these partial slopes one at a time, right? So we can still look at the model as a whole and say this whole model, kind of as a package deal, is useful at predicting. You can, I guess, peek at these estimates to come up with the prediction expression and plug in numbers to make your predictions. But that's where you would stop. I mean, you could describe the fit with R square and root mean square error, but you wouldn't want to estimate the partial slopes like formally with a confidence interval, or you can't even really trust these t-tests either. Okay? So when it comes to trying to parse out, well, what's the contribution of acceleration versus what's the contribution of quarter mile, we just can't untangle them because they're so strongly related. All right, so checking that none of the correlations among the predictors are strong, absolute value greater than 0.7 is a good way to check or prevent strong multicollinearity from happening. A little bit more sophisticated way is to add in what we call the VIF, or variance inflation factor. So each predictor has a VIF. This is the formula. So the VIF for your one predictor, go one at a time. So weight, acceleration to 60, quarter mile. You would take 1 over, 1 minus, and then this r squared sub I is what would r squared be if this predictor was actually the response variable. So let's say for weight. If we wanted to calculate the VIF for weight, we would say, all right, let's let weight be the response variable and use acceleration and quarter mile to predict it. What would be the r squared? So that number would go here, and that would tell you the VIF for the weight. And then JUMP is going to do this again for acceleration. It's going to say, well, what if acceleration was y and weight and quarter mile were the x's? All right, so you won't have to calculate this by hand, but just letting you know a little bit of what's going on behind the scenes. And the rule of thumb with VIF is we don't want VIFs above 10. So above 10 is, severe multicollinearity. Now, again, you could still do predictions. You could still pretty much just do predictions, but you wouldn't be able to do anything with the specific partial slopes. All right, so above 10 is really bad. Between 5 and 10 is borderline. So still, like, you might put a little caveat if you did interpret the partial slope. You might do it, but mention that there were some signs that there might be some multicollinearity present. So to add these in, after running your model, go to that parameter estimates table, right-click in the body. So remember, we did this before. We went to columns. We previously saw how to do confidence intervals for the partial slope, so using the lower and upper 95%. But down a couple rows, you'll see VIF. All right, so the intercept doesn't have a VIF, so that'll always be blank. it looks like weight has a VIF of about 1.44. So that's good. It's below 10 and it's below 5 also, so no concerns about weight being in the model. For acceleration, though, and for quarter mile, they are both really high. Now, part of the reason they're both, I guess, in the low 70s is because they're really correlated with one another. But this is also, remember, looking at the fit with weight in there as well. Okay, so they're not going to be exactly the same. Right, but they're both above 10 and by a whole lot. So that's your sign that, one of them's got to go if you're interested in, say, coming up with a real estimate of the partial slope for weight or for acceleration. You'd have to take quarter mile out. Or if you're interested in quarter mile, you'd have to take acceleration out. All right, so to put everything together, building good models is really an art form. So I recommend always starting with the scatter plot matrix. Remember to check for linear relationships and to do like a first pass against multicollinearity. Then there's two approaches to model building. There's what we call the forwards approach, where you kind of start small and add things on. Or there's the backwards approach, where you put everything in and then start taking away. So we've been working with data sets that don't have usually too many columns aside from this CARS data set. But, so especially when you only have like, say, a handful of predictors, 3, 4, 5, 6, a good strategy is to try adding them all. And then gradually, one by one, removing the predictor with the largest t-test p-value, the least significant predictor. Do it one at a time, because we know that as you remove, the other p-values are going to move around a little bit. But then keep going until you've got all your p-values at a level that you like. So a lot of people use below 0.05, but depending on what you're doing, this could be below 0.10 or even below 0.01. But just come up with some consistent threshold. Then take a look at the residuals once you've got the predictors that you think are all significant. If your residuals show any funky patterns, then you might need to take some action. So we saw that in the diamonds example, if the variance was not constant, we saw that funnel shape, that maybe a variance stabilizing transformation could help. So we did the log transformation on the y variable, and that did the trick. Or in the clocks example, our first order model had some non-normality in the residuals. But when we added an interaction term, the residuals became more normal. So that was the missing link there. All right, then finally, as a kind of crowning glory, add in those VIFs and confirm that none of them are above 10 if you do want to do anything with the partial slopes. And like I said, between 5 and 10, we'll allow it, but we may want to just communicate to people that, hey, this model has a little bit of multicollinearity. You could always try removing one of those predictors anyway and see how much your model really changes in your predictions. So that concludes multiple regression. In an ordinary semester, not affected by the coronavirus, we would have had one more lesson on quadratic models. So if you're interested more in multiple regression, I know, humor me for a second. If you want to do a little bit more, I would suggest that quadratic models would be the last kind of essential part of multiple regression for your toolbox. Thanks for watching.